This is a production of Cornell University.
Thank you so much, Jenny, and thank you all for coming. I'm really excited to talk about this today. My title is Solar and Agriculture from Competition to Co-Location. So I'm really going to be trying to focus on ways that we can build bridges between some of these different land uses. Just a little bit about the structure of this talk. I'm going to start with a section that's kind of just the big picture about solar and siting. What's our outlook for solar? What kind of challenges do we expect to face in land use for solar? And how do what I'll broadly call innovative siting solutions fit into that challenge? Then I'm going to really focus in on agrivoltaics, the practice of combining solar and agriculture together. I'll talk about sort of what those technologies look like, why we think they're interesting, and what some benefits might be. Then I'm going to talk a little bit about our research portfolio at the Department of Energy that specifically focuses on solar and agriculture. So, one thing I'll get into a little bit is I come from an applied research office, so we're really focused on enabling and pushing technologies forward more than we are on the regulatory side. All right, so let's talk about solar and sort of solar from a strategic perspective. The story of solar in the last 10 years that is kind of really important to wrap your head around is rapidly falling costs and rapidly rising deployment. So some of this is obviously due to policy pushes in terms of climate goals like New York's or others, but some of this is all, but I really want to emphasize the degree to which the cost of solar, which is here, it's the right axis here in the line graph. You can see that the cost of solar on a per kilowatt hour basis fell from nearly 30 cents a kilowatt hour in 2010 to down near 5 cents a kilowatt hour in 2020. I'm not sure if we have 2021 numbers out and finalized yet, but that's been accompanied with really rapid growth in the sector. So in 2010, you can see here, this is in gigawatts of capacity. You're seeing, I don't know, 1 or 2. And that's ramped up in 2021. The projection was that we would install about 120 gigawatts of utility scale solar. So that's the story of the sort of 2010s in solar, and is really remarkable just in terms of how different the economics are from what we were talking about. And this really is due to scale up in manufacturing as well as favorable policy environments. The result of this is that now when we look at 2021, solar is the most common new source of generating capacity. So when you look at what was added, this is from the Energy Information Agency. If you look at what was added nationwide, nearly over 15 gigawatts of solar were added. That outstrips wind, natural gas, batteries, nuclear, and other. And so as a result, you can see that solar is becoming rapidly one of the largest growing sectors of the energy industry, and really starting to take on a much more prominent role. The prominence of this role we really explored in a report that we published last September called the Solar Future Study. So Solar Future Study is this report that my office created in partnership with the national laboratories that really started trying to chart a pathway to providing large amounts of US electricity through solar by 2050. So we're currently at about 3% of the electricity in the US comes from solar energy. This charts a pathway to 45%. And it looks at basically decarbonization pathways, achieving 95% decarbonization by 2035. So this is not one where solar is the sole energy source. I don't think anyone is really aiming for that, but one where solar is in some ways maybe the dominant energy source. So in these scenarios, there's a couple of them. There's the reference scenario. There's a decarbonization scenario where we sort of work very hard to decarbonize the power system, in which and then there's Decarb plus E, in which we not only try to decarbonize the power system, but we also focus on electrifying loads. So converting vehicles to EVs, converting heating from natural gas to electric, heat pumps or things like that. And so in these scenarios, you see that we go from 80 gigawatts in 2020 to a terawatt potentially in 2035, maybe a terawatt and a half by 2050. There's a lot more solar development coming. And I also want to emphasize it really comes to new places. So if you look at it in the early 2010s or mid 2010s, maybe the major capacity was deployed in like California, Nevada, Arizona, these big sunny places, lots of deserts. And we're really seeing already that's starting to change. I think California is no longer the largest state for solar capacity deployments. I believe it's Texas now. But you also see Florida, Georgia, the Southeast really coming up. And in the long term, in these high solar development scenarios, we're seeing more solar deployed in these census regions that currently don't have very much, such as the Northeast and Midwest. So these places that now don't have very much will have more solar in the future than California, for instance, does today. And that brings us to the land use challenge. So solar land use, I don't want to oversimplify it. It's really varies a lot based on panel efficiency, how the plant is laid out, the latitude you're at. Further south, there's more sun. My rule of thumb is 5 acres a megawatt, basically. So we're talking about a terawatt. That's a billion watts. So we're talking about millions of acres. So when we look into what we're looking at in these scenarios, we're really seeing land use increasing to 2035 to up to about 5.7 million acres, to as much as 10 million acres nationwide in 2050. That would be about 0.5% of the US land area, which would be larger than the state of Maryland, as you can see from this graph. So I want to this is the tension that we sort of live in, I think, in the solar land use discussion. 0.5% of US land area, it pales in comparison to some other land uses, such as the amount of urban area and paved roadways we already have. Even the amount of previously disturbed land is much larger than that. There's also a very sizable chunk of this that, maybe not all of it would be like contaminated land or brownfields or things like that. So, compared to the total land available in the US, maybe it doesn't look that large, but 10 million acres is still obviously quite a bit of land. And it's not going to be evenly distributed, right? There are certain places that are closer to transmission lines, have better climates or flat or whatever, that are going to experience this more than others, and that's going to lead to some local friction. Some friction is to be expected, and I think that is maybe a little bit of a soft pedaling of it. We're really starting to see this as a major concern for the industry, as there's various local concerns and increasingly organized local opposition to some of these projects. So some of it is really about preservation of prime farmland or prime forest land. Some of it is about concerns over health impacts. And these are all, tied up very deeply with what an individual community's feels as its identity, as well as kind of where the local economy is at. And also, what other land use changes are kind of causing concerns. And these are also very deeply bound up, I will say, in what the individual community's zoning and land use policies are like, which vary greatly from place to place and state to state, obviously, in how they are structured. So, there's lots of ways forward on this, I think. I don't want to, as I said, we don't want to frame land use as an absolute constraint. There is enough land to accomplish this energy transition. And so most of the solution will probably still use traditional solar siting on green fields. I mean, we need to get better at things like learning how to facilitate regional and local land use planning to minimize that conflict, to structure projects so they provide benefits for communities. They're not just seen as some developer coming in and doing whatever they want without concern for the neighbors. We need to build things like mapping and screening tools that can be used to identify good sites early on, and really provide clear guidance both to the developer side and the community side to help everyone understand the trade-offs and negotiate through this development process. But one thing that's also really interesting, I think, are this broad category of solutions that we call innovative siting solutions. These are ways to site solar energy that use sites kind of other than greenfield development. So the idea is that these developments will take pressure off of undisturbed land and kind of expand the space of where siting can go and open up new possibilities for communities. And some of these may even have some unique benefits that go beyond just electricity. So some of the ones that we might hear about are things like brownfields. So this is the construction of solar on former industrial sites or former mine lands, for instance. Floating solar is increasingly popular, I would say. So in this case, solar is put on some kind of pontoons, and there's a lot of interest using this, for instance, on hydropower reservoirs, on canals or things like that. This is a picture of mine land development. Again, DOE actually has a very large program for demonstrating renewable energy on former mine land that came out in the infrastructure package. That's not what I'm going to be talking about today, but I'm also very involved in that. And then canal solar as well is something that's being tried in California. I think one of the interesting things about some of these water-based solar solutions is they can also avoid evaporation and potentially result in some water savings. But the one I'm going to be focusing on today is agrivoltaics. So agrivoltaics is the combination of crop and livestock production or pollinator habitat underneath solar panels and or in adjacent zones around solar panels. Agrivoltaics is kind of a recent term, and I'm not sure the field has really stabilized on calling it that. You'll also see it called things like co-location of solar in agriculture, dual use of solar, ag PV. I feel like every time we run some kind of solicitation on this, everyone who proposes a project names something different. And the key idea here is that, yes, we're going to have some trade-offs, but the hope is that we can make those trade-offs sort of work. So, you're going to have less light and you're going to have more difficulty farming. You're going to have to kind of navigate these panels. That probably means you're going to get less crops or less agricultural product of whatever kind. That might not universally be true, but I think that's a fair assumption to make. Simultaneously, you're also going to have to space the panels out or make them semi-transparent or something like that to let some light through, or to let farm workers in underneath them, and that might lead to less electricity production. The hope is that if we can do both of these things, then we can win at kind of the system level. So this is a diagram I stole from Fraunhofer in Germany. You see on the left, they're saying, okay, you can imagine having 2 hectares where one is all wheat and one is all solar power. That's all well and good. Maybe you combine them, you're getting 80% of each, but you're doing it on half the land. And so it's 160% efficiency in comparison. And so this kind of question of can we build solar or plus agriculture with this kind of favorable land equivalent ratio is really, really important from an economic point of view to minimize the land impact of solar energy and of increasing this compatibility. So I'm going to walk through now some of the major modalities we see for solar and solar plus agriculture. So one is pollinators. Pollinators are, I would say, one of the more advanced versions of this, in the sense that many states are really pushing this on the policy level. So, the traditional solar plant, or the sort of most standard one, might plant turf grass or some kind of easily mowed and managed grass system. Many people are now pointing to the possibility to use solar fields as a source of habitat for pollinators, such as birds and bees. It's estimated that about 23% of US crops depend on animals for pollination. It's also further estimated that there's about 3,500 square kilometers of agricultural land that's near current or planned solar developments that could benefit from this pollinator habitat. So the idea here is that by planting these more robust kind of ecosystems around the solar panels, you provide ecosystem services to nearby land. You also have some other possible benefits. For instance, there's some studies that we're starting to see that show that this may help with water runoff management, because you have deeper rooted plants that can help with infiltration. There are downsides, however. The solar developer will now have to establish this habitat. That means buying special seed mixes. That means sort of maintaining it for a few years, especially as it gets established. And there's a lot of concerns about finding a mix of seeds that works with solar in particular, that doesn't get too tall, right? I mean, if you start shading these panels, you see production drop quite a bit. So this is something, as I said, we're seeing some state policy moves on this. 8 states have created pollinator scorecards to encourage solar facilities to adopt these kinds of practices. Grazing is another really exciting one, I think, that is also starting to already see some commercial purchase. So if you have an animal that grazes, you can do it at solar farms. One thing that's really interesting is that grazing is not just a matter of saying, well, we're going to use this land for something else. It actually serves a purpose to the solar operator, which is that usually you have to mow these things regularly to make sure that the vegetation isn't, swallowing up your solar panels. And there's potential to use grazing to supplement or replace that mowing. In some cases, the cost can be lower. That's really site dependent. And there's evidence that this increases, that grazelands have increased soil carbon and some other positive impacts on kind of the grassland ecosystem as well. So, as I said, we're already seeing actually a fair amount of commercial practice for this. I believe actually, especially in New York State, the dominant commercial practice for this is sheep. So lots of people are interested in cattle because there's more cattle than sheep raised in the United States. But these larger animals, they raise a lot more concerns about panel damage. So the idea here is that the animals get a chance to graze this. They get forage. They also get, for instance, shade. That could be a really important climate adaptation technique potentially. And farmers actually get a new revenue stream. So the business model we're seeing emerge for this is one where grazers are going to solar sites, having their herds graze and getting paid for that service, which is a really interesting flip from leasing pasture land to actually getting paid to go graze. So finally, the third category I'm going to talk about is crops. So crops is obviously, I think, maybe even what comes to mind the most when people think about agrivoltaics or agriculture around solar panels. It's a lot harder, I think, than the pollinators are grazing, and therefore it's a little bit less, I would say, commercially advanced, although we're starting to see installations kind of at the megawatt scale or smaller. So with crop agrivoltaics, we're talking about growing crops that could satisfy food, fiber, or bioenergy needs, really looking beneath or around panels. This unlocks potentially a very large amount of land, and there's evidence that the shading can provide some drought resistance and potentially save water. There's some really interesting work out of Greg Barron Gafford's group in Arizona that's really looking at how this shading affects growth in, well, Arizona. And there's potentially significant impacts on water use efficiency and things like that. There's also potentially some back action on the panels. The transpiration from plants can cool panels, leading to a better microclimate directly beneath them. And that cooling actually improves the efficiency of solar panels. There's a lot of challenges to crop agrivoltaics, and I think that it's worth really discussing what these are, because this is such an interesting area to people, but it really is one that's still, I think, in its infancy. So some of the challenges that we're looking at trying to solve are, one, and this is kind of obvious, but it's worth saying, is plants need light to grow. So pretty much any agrivoltaic solution you hear about is trying to figure out a way around the question of splitting up the sun between electricity production and plant production. One way is just to use shade tolerant crops. Many crops do not necessarily need all of the light that they would get in a given day. And so there might be ways to, so there are usually ways to adapt to this, but we see people trying to use things like semi-transparent panels, which may or may not be wavelength selective. So some people are trying to work on panels that specifically filter out only wavelengths of light that plants cannot use in photosynthesis. For the most part, we're also just seeing spacing the panels out. So you see this installation here on top is, I believe, at the University of Massachusetts. And this is an installation where they're growing, I think it's kale or broccoli. And these panels are simply at a larger spacing. So you're getting less power per acre out of this site, but you're allowing the plants to capture more of that light. Finally, tracking. So this refers to the tracking for solar panels means whether or not they actually move with the sun and follow the sun. Many solar panels track, and that can be used to sort of shift in the shade and perhaps allow light in at certain times. If there are certain times of day that the plant might be better positioned to benefit from it. And I would say the second really key challenge that we see talking a lot is equipment capability or compatibility. So how do you mechanize farming when you're having to steer around all these solar panels or all this electrical infrastructure? So there's a couple different solutions to this or ways to go about it. The main one is using smaller equipment or hand harvesting plants or plants that are mainly dealt with by hand. That could limit the scaling of this solution. Certainly one thing that I've been asked a lot when I give talks about this is, can we do this with corn or wheat or soybeans? And that seems very difficult at this time, but we can keep hope alive. So that's why you mostly see these, right now you're seeing these proposals more around peppers, tomatoes, broccoli, kale, things that are not harvested with a massive combine. And then finally, you can maybe alternate rows of crops with rows of solar panels, which is what I believe, what you see in this bottom picture here, where you kind of have equipment-friendly corridors around the panels. So that one is a little bit less maybe integrated in terms of land use, but it does permit some of these more mechanized approaches. So the hope really is that agrivoltaics as a solution could deliver benefits to a large number of people. So when we talk about the different sort of stakeholders in this process, for farmers, we want this to be a source of new revenue streams. You essentially have a new crop, electricity, a source of drought resistance and water use efficiency, where we're looking at adapting to potentially increasing aridity in response to climate change, or just needs to limit water due to aquifer depletion or things like that. Pollination of nearby crops. If it's a nearby pollinator solar habitat, you may see crop benefits even if it's not your land. And then finally, on-farm energy production and resilience. So ways to generate energy on farm both may reduce electricity costs for the farmer, but they may also provide a new source of energy that does not, that may be harder to interrupt or may offer some backup power in times of storm or if there was grid issues. This is especially important considering that many rural areas have a more failure-prone electrical grids than we might experience in cities. From the solar point of view, there's a potential for more efficient vegetation management. So one of the main things that solar operators have to do is maintain all the grass or vegetation around the field. So if they're grazing or people are actively managing it as a cropland, you might be able to get some efficiency there. A potential for, as I mentioned earlier, cooling the panels off, providing a favorable microclimate. Water runoff management, I mentioned this earlier, but basically vegetation of various kinds does improve stormwater runoff management and maybe a favorable strategy for that. And then finally, community acceptance. So as we're thinking through rural and agricultural areas increasingly being asked to host these sites and seeing, I think, on a number of levels in a number of states, concern about solar energy production displacing agricultural land, this may offer a solution in which agricultural land does not have to be displaced and can be, sort of strictly speaking, an economic enhancement. And so, from the community point of view, we want to think about what they might be gaining, and one is potential for the pollinator deployments. For instance, we might see pollinator habitat or wildlife compatibility, maintaining agricultural land where that's important in communities, which I think we see it certainly is. Providing jobs and economic opportunities. So this provides a way perhaps for communities to reap the economic benefits of a solar installation, as well as the agrivoltaic benefits. And then finally, climate mitigation, right? This is ideally low or zero carbon energy production, and we may even be able to see some carbon sequestration depending on the sort of cultivation practices. So some of the major challenges that I think we're looking at right now are system design. So you have to combine designing a solar power plant with designing an agricultural system. Those are teams of people who are not necessarily used to working together. So we're really working on building those teams that have the expertise needed to do that. The agricultural design is really region specific and even site specific. You need to take into account the soil, the climate, all of that kind of thing. And so it makes it very difficult to kind of say, well, this is the one way to do it, which is maybe a little bit less true for solar energy, right? Where the sun shines, is the sun shining. You might need to adapt for the region specifics, but maybe less site specific. We also see a lot of challenge in scaling this. So thus far, if you look at agrivoltaics installations, the dominant form has been kind of small research scale sites, really just proving this stuff out. So really understanding how we make this work at a scale that matters for siting, right? I mean, we're talking about millions and millions of acres. So how do we make this work at a scale that can actually affect something? And then finally, there's a lot of economics questions here. So here we basically we have the underlying land, we have the photovoltaic system, and we have agricultural crops and assets. So there's a lot of questions about who owns what pieces of this, who leases what pieces of it from who, how does the money actually flow in the situation? This is kind of key to figuring out if it's going to attract farmers and if it's going to actually benefit farmers and communities. And honestly, it's something that just kind of has to be worked out to some degree, but we're already seeing some people really dig into this. I would point to, for instance, if you look at the American Solar Grazing Association, is a great professional association that does things like publish sample contracts that grazers can sign with solar developers and things like that, that really help standardize kind of how these business arrangements work. There's a lot of open questions. We don't know things about the long-term impacts of soil energy infrastructure on soil quality because it's such a sort of new form of development at this scale. Trying to identify what crops work for this, I think, is a major question. That's going to depend on shade tolerance, temperature effects, all kinds of other things. Again, the system design question: how do you co-optimize? We know how to farm, we know how to build solar panels, and we know how to do both of those kind of optimally and how to really squeeze every last drop of production out of either kind, but we don't really know how to build them to work together. For grazing, there's a lot of questions about how animals will interact with solar energy equipment. Like I said, sheep are more common for this purpose. With cattle, there's more concern. I've heard stories from people who have tried goats and found that goats like to jump up on panels and play around, which sounds adorable, but it probably is not really good for the panels. And then finally, again, figuring out these business and contractual arrangements is I think, a really key open question. Okay, so I'm going to take a brief tour through some of the research that we're already doing here at DOE. And hopefully this can give you a sense of kind of where we've been making our investments and some things we're excited to see in the near future. But first, let me give you a little bit of a tour through my office just to explain what it is we do here. So we're really working on advancing and deploying solar technology to decarbonize the energy system by 2050, starting with decarbonizing power by 2035. That means we're trying to make solar technology more affordable and accessible, making it support grid reliability and supporting job growth, manufacturing, and circular economies. And we kind of fit down here at the bottom of a long hierarchy that runs up through the Undersecretary for Energy, then the Office of Energy Efficiency and Renewable Energy, and then finally we sit within a particular Office of Renewable Power. So some of our sister offices are like the Wind Energy Office, the Hydropower Office, and the oh man, I'm blanking. Well, oh, the Bioenergy Office. That's and geothermal. So we have a number of teams in our office. The two that are most involved in agrivoltaics are strategic analysis and institutional support. So this is kind of our soft cost team, really thinks through these high level issues like land use, and manufacturing competitiveness. This is a team that really works to support early stage businesses and kind of works in the startup space to help people commercialize new technologies. So we're really working on a number of different things, whether it's energy science and field work, conducting analysis, doing kind of the social science, building communities, and also developing this technology and validating that it actually works. And that spans both kind of when we think of conventional technologies, which might be sort of ordinary photovoltaics with maybe some spacing between the panels, all the way to new technologies where we see things like these proposals for semi-transparent panels or other types of really innovative hardware types. So our flagship program is a program called Inspire, which is hosted by the National Renewable Energy Laboratory, along with Argonne National Lab and a nationwide partnership. Inspire is working to build a network of research sites, companies, and universities that are interested in agrivoltaics. And they've been running for a while now. I would say Inspire first started in actually 2015 and has been doing field research, analytical studies, building out this working group, and building a great website where they've been collecting data and research information, as well as a lot of resources for people who are interested in getting involved in this. And you can see this is a map of their project sites, and you can see that they've really done work all across the country in various types of kind of across the categories I've talked about so far, and this is only expanding. So Inspire 3.0 is the newest version of Inspire. So we kind of have demonstrated, I think, that agrivoltaics is viable, that the basic idea does work at research scales. And we've built this really valuable infrastructure of a network of test sites and a network of people who are interested in this. And the goal is really to try to map and address the remaining knowledge gaps and prepare the sector to start expanding much more greatly. This particular program is going to run for the next 3 years. It just started a couple months ago and is about $3.75 million for those 3 years just to this one project. This is about a doubling of their budget from the last 3-year cycle, which I think hopefully speaks to our growing interest in agrivoltaics and site preparation. So some of the things they're doing to foster this community is to maintain the Astro Network, which is their group that connects researchers, advocates, and industry to provide feedback and guide the research program. They're going to be funding seed projects, grants of just like a few $1,000s each to help students get started in agrivoltaics. And they're doing a lot of interagency collaboration. So we know we need to be talking to USDA, certainly the Department of the Interior, National Science Foundation, and others, really to help build out a federal complex of people who can support this type of land use. They'll be providing a lot of work to sort of help the research community as a whole, such as tracking different sites. Right now we don't have a centralized database where we can look up and see what agrivoltaics is happening in the US. So we kind of have to estimate. This is going to make it much more rigorous. They're going to be performing research needs assessments and roadmaps and conducting economic analysis to understand the challenges in scaling to these multi-megawatt installations. And then, they're going to keep on doing a whole bunch of field work. So they'll be evaluating agrivoltaic systems in many different sites and conditions, over looks like 7 states. They'll be looking at vegetables, cotton, as well as they're working with a couple tribal nations to look at traditional tribal crops. And the goal is really to find and recommend what systems work best for this. We don't expect all production to convert into this on either the solar or the agricultural side. So figuring out sort of the Venn diagram where this really works is I think, best. They'll also be conducting ecosystem services analysis, really focusing on pollinator habitat and solar in a number of states, looking at soil science and soil conservation impacts of solar, and starting to look at bifacial photovoltaic panels. So those are panels that generate from light that hits the back of the panel as well as the front. There's a lot of interest in this, partly because plants may be you could look for plants that are like particularly reflective, for instance, that may provide more of that bifacial advantage. The other group of things that I'd like to talk about is a bunch of projects that are coming out of a funding opportunity we launched in fiscal year 20. This was a $7 million funding opportunity. We have 4 awards in this bucket that are all going to last 3 years, and they're really focusing on expanding agrivoltaics into new places, into new communities. So I'll take you through a quick tour of some of these projects, which are in general smaller than Inspire and more focused on particular regions, but certainly just as important. So the University of Massachusetts at Amherst, through their Clean Energy Extension Office, is working on doing yield and soil impacts on a number of different types of crops across the state of Massachusetts, looking at economic analysis to understand what this will do to farms as an individual, as well as rural economies and sort of the farm sector as a whole. And what's really interesting about this is that Massachusetts has, as far as I know, I think one of the most aggressive state programs to encourage agrivoltaic development. In particular, they have about, I want to say it's 6 cents a kilowatt hour added to their feed-in tariff for agrivoltaic installations. So they're really providing the economic incentive for people to make these installations, and there's a lot of interest in pursuing this. Silicon Ranch Corporation in Georgia is works on regenerative agriculture and solar plus grazing sites across the Southeast. They've really focused on sheep so far, but of course they're really interested in cattle. And this is a project that's going to focus on animal welfare testing and soil science monitoring of rotational grazing systems with cattle in Georgia. They're really focused on tracking the carbon that's stored in the soil to develop new types of hardware and tracking schedules that really facilitate solar plus cattle grazing. University of Illinois at Chicago is focusing on pollinators, particularly large-scale solar facilities. So, pollinators thus far have been very focused on, have been more focused on the smaller end, and these large-scale facilities, 10 megawatt or larger, have been a little bit less clear as to how we can make pollinators work with potential additional costs. What does it take to really set up these pollinators? How does the need for pollination change when you want to do, hundreds of acres instead of just a few dozens of acres? And so they're really focusing on how pollinators can work at very large scale solar sites, specifically focused in the Midwest. Finally, the AgriSolar Clearinghouse from the National Center for Appropriate Technology. So NCAT is a technical assistance group and really does a lot of great work helping people with agricultural technologies, helping people get started in farming. And they've set up this website and this site called the AgriSolar Clearinghouse, which is really focused on information sharing, peer-to-peer learning, relationship building, for agrivoltaics. So if Inspire is really focused on bringing together the researchers, NCAT is really bringing together the practitioners. I really encourage everyone to check out this website if this talk sounds interesting to you. They're doing a lot of great work. They're producing a lot of media in the next year, and they're doing site visits to a number of places across the country, which you can register for and tag along if you'd like a tour of some interesting agrivoltaic sites. We also, as I mentioned, fund small businesses and startups. These are much more on the hardware side. So we've done one small business topic on solar racking and mounting design, and one on solar powered aeration for aquaculture. We've funded a number of companies in these areas. So I want to wrap up and make sure I have time to get to questions, but I do want to flag some things that might be opportunities for you to engage if this is something that you or your organization really want to get involved in with us in our office. So Inspire has this group called Astro that does quarterly meetings where they present research, where they help develop new research sites and activities. They provide feedback on research directions. And as you can see, we have a very large number of collaborators here, spanning from ag to environmental to solar research and state agencies. Yeah, our team is always hiring. This picture has been taken several years ago now, so it's kind of funny to see because it's kind of outdated. If you know a student who might be interested in working in a DOE's office, particularly post-graduation, there's the ORI Science and Technology Policy Fellowship. It's very focused on helping us implement and design these R&D programs. And this is a great program for especially new graduates. This is how I first joined the department, actually. Please feel free to reach out if you'd be interested in this. Finally, if you just want to keep up with the solar office's work, we have a newsletter where you can sign up and get, I think it's about a monthly email about new funding opportunities, publications, and events that we're hosting. We also host regular webinars to kind of broadcast some similar information. So I think I can wrap up there, and I'd be happy to take questions now.
Thank you so much, Zach. That was fantastic overview and super informative. I am going to start with Rosemary Lee's question. I am a beekeeper. The idea that pollinator habitat can exist under solar panels is not feasible. None of the sites that we have seen so far in New York install these habitats. The areas have to be mowed and maintained to access the panels. How are you seeing this happening? It sounded great, but it's not happening unless a completely different location on the site, and most solar installers want to use the entire site for solar production. Thank you.
I think that we're seeing. I'm not aware of the status in New York, so I'm a little bit unclear. I think we have some opportunities to work with this as we go through the UIC project, which is really focusing on these large scale sites. You're right that many operators want to devote the entire site to solar production. I think at the state level, we're starting to see more states, and I don't know about New York specifically, focusing on production or focusing on ways to encourage pollinator habitat or compatibility. I know there's at least one company out there that's selling honey that they at least claim was entirely grown with pollinator habitat on solar sites. So I'd be happy to try to connect you with that. I think that this is still very early days yet. So I don't think it's happening at large scale or even at most solar sites. This is more something we're still trying to enable.
So David K asks, about 60% of US farmland is owner operated according to the 2017 Census of Agriculture. And it has been fairly stable over longish periods of time. This raises issues of one, split incentives for agrivoltaics where the land is not owned by the farmer, and two, changing value of the land that increases the incentive for non-farmers to own land currently in farms. Any work on these questions going on?
Yeah, I think so. For one, I think that's for split incentives, I think that's definitely a major question. I think that is one of those things where it may be that perhaps it only works for owner-operated farmland. But I think this really is somewhat up to the industry to discover what commercial practices might actually work here. And I think that's going to be a difficult question. I mean, we see the same thing, for instance, in rented homes as well. There's this split incentive program. So I don't think there's an easy answer to that question. I think it's something that will kind of depend on what economic opportunities actually emerge and where those benefits actually fall. I think the work I've seen, so certainly in grazing and in some similar, for instance, okay, so in pollinators, it's less about finding a dedicated farmer. In grazing, we're seeing more of this service model emerge. For croplands, I think it depends. I think we haven't really seen what the commercial models look like for that yet, so it's a little bit difficult to answer. In terms of changing value of land, I think we know very little about that, to be honest. We don't know enough about how this type of development impacts land values in the long term because too much of it is too new.
I'm going to follow up with a personal question. So what do you think about activating this idle or marginal or underutilized land that Peter was talking about at the beginning, which may not be associated with farmers? Like how is the national perspective looking at engaging non-farmers in activating these shrub or other land areas?
Yeah, I think it's an interesting question. I mean, one thing that's a little bit tough is that I think the land use discussion from the land use side is sometimes not the one that. So if you talk to developers, for instance, about how they find and try to identify land, is the primary driver of that is often transmission access. So where is their transmission capacity? Where can I plug into the grid? And that kind of puts us sometimes on a back foot because we're being reactive to that need. And so we're really trying to find figure out what trying to figure out how we can find lands that might be useful for solar that also sort of meet these commercial goals as well as kind of maybe meeting other land use goals. So this is part of what I mentioned, that there's been some efforts, I think, to pre-identify land that might be useful for solar, or to kind of, you can imagine sort of stoplight systems where we say, okay, don't develop here, do develop here, try not to develop here, things like this. There's a lot of concerns, I think, with this, in part because you need really good data, and it's very hard to say, well, are you really taking into account everything that you need to know to do that kind of thing? To really be able to say for certain the development will or won't work in a certain place. And then I think the final thing that you might think about is we are seeing some states, I think, sort of try to provide incentives or directions on where they'd like to see solar development. So that's, I mentioned Massachusetts has this feed-in tariff program for agricultural land. It actually is, or not for agricultural land, but for dual use agrivoltaics. It also deals with a lot of other stuff as well, I would say. So for instance, landfills, I know, are one. They encourage solar development on former landfills. So these capped landfills, often the ground is not really stable enough to build housing or things like that on it, but it can be used for panels. So we're working on trying to understand better what that what kinds of policy impacts or what kinds of policy landscapes influence those land use choices.
I'm going to follow up quickly with one more because we've got some more time. What is the national perspective on, if we're moving towards electrification, how can we think about the next generation of grid development to facilitate both energy security for citizens, but then also this initiative for developing the renewable portfolio?
Yeah, it's a good question. I mean, I think you sort of have two different kind of perspectives on this. I mean, one is about large scale transmission lines, just trying to balance whole regions and kind of between states. And that's certainly one need you see to make these kind of renewable grids feasible. It gets much easier if you can move power very easily across the country. And then kind of on the local level, you also see a need to adapt to new higher loads, especially, I mean, the two things that people talk about the most are electric vehicles and the need to be able to handle the high loads that might come with charging up if you need to charge a vehicle quickly. And then the other is heat pumps, especially questions about like, well, you know, just before sunrise, before the solar comes on, it can be quite cold. If you have an electrified system, you might suddenly see a really clear need for more generation there. And that's a grid challenge as well, I would say, is making sure that everyone can actually access that electricity.
So Brian Aldrich asks, one hopefully minor but practical issue to address is weed control under and around the immediate perimeter of the panels. There are time and material costs required for this task. Hopefully the revenue stream will cover these costs. I'm curious to hear how farmers are handling this. Got any stories?
Yeah, I don't know if I have any particular stories. I will say that, you know, the thing is, for weed control, is the solar fields are always going to have to deal with weed control, right? Like the outside of agrivoltaics, you're having to spray or mow this whole field. And so if there is still some weed control left after, you know, some of it is devoted to cropping, then I think that it's kind of a question of what baseline are you measuring it from. And so it can maybe be looked at as a fraction of the cost that you would have spent on weed control, perhaps otherwise. I don't know about particular practices people are using for this quite yet.
Jen Blair asks, how do solar panels impact the soil? There must be compaction, erosion, and the need to build an access road for maintenance. Over a 20+ year period, how does this impact the land from ever returning to growing crops?
Yeah, I mean, that is a really great question. I think that's certainly one thing that we're still trying to understand. I mean, I think that the truth of the matter is it hasn't been studied as much as maybe it needs to be. Some points on solar compaction. I will say that this has been addressed somewhat by people who are working in the brownfields sector, where often there might be soil that is for contamination purposes. You really don't want to disturb it too much. And I've seen that there have been some really clear guidelines developed in that sector for avoiding erosion and runoff in those cases, looking into things like just limiting weight and things like that. So in the landfill and brownfield sector, you see some people dealing with that. In terms of in the long term, I think the thing is that's important to understand is there's a really wide array of solar practices that can be used during land development. And part of the question is also what practices are people actually using and what would be the additional cost of adopting, less impactful or more soil conserving practices. And part of that, I think it can hopefully be assisted by saying, hey, we do want to maintain this as an agricultural land either now or in the future. Because the one thing we have talked a little bit about is whether or not solar, so the lifetime of solar plant is about 30 years. So one question is, can this be something that is used, temporarily, and then we say after 30 years, we're going to pull this out and resume cultivation on this land, maybe after building some soil for those decades. And I think that sort of remains to be seen. We're still working on it.
Roberta Nilsson says, relatedly to Jan's question, I'm curious what is known about the impact of large-scale PV on local water resources, such as whether water is needed to clean the panels, how water drains off the panels, and any impacts to water resources based on the digging, drilling into the poles. Are these questions that have been answered and researched, or is it ongoing?
Yeah, so we have research on some of these. So for cleaning the panels, I think the answer is yes, but not frequently. So there is panel cleaning, but it's not done very frequently. It might not be done at all, actually, in states with higher rainfall. So but it is something that is often done in sort of dustier, more arid climates. One advantage is that there's no need to use drinking water quality water for that. I have seen some suggestions to use sort of gray water or things like that. I also know that I've also seen proposals to recycle or otherwise gather or collect that water and perhaps use it for either watering in an agrivoltaic setting. So, clean the panels and then irrigate with that water, or potentially just collect it for some other purpose. For water draining off the panels, this is a really interesting question from a stormwater management perspective. We do have a project called PV Smart at NREL, which is, I don't remember what the SMART stands for, but it stands for Stormwater Management something or other. So if you look that up, I really recommend it. They've been doing a lot of work, especially looking at like local zoning officials and talking to environmental regulators at the state level to try to understand, what are the impacts of solar on stormwater runoff. You do potentially see like increased erosion at the drip edge of the panel, but maybe there are ways potentially to alleviate that or to work against that or to try to counteract that. Finally, for impacts to water resources based on digging/drilling in the poles, I'm not really aware of that. I mean, I don't think that they're usually deep enough to impact groundwater with that, but I'm not sure. I'm not aware of any research in that area.
David Bem asks, any research or insights on potential of battery storage sites that would not be located near transmission lines and where the generated power would be temporarily stored until it is dispersed to users from the solar generation site?
Yeah, so that's like kind of an off-grid or maybe you call it microgrid solution. I mean, I think it's certainly very interesting. Those solutions tend to be, well, it's not to say, like, so if you look at the microgrid stuff, often in isolation, you say, wow, that's so expensive, but because you have to build all this extra storage and all this kind of management and the kind of electrical infrastructure. On the other hand, if you're way out there and you're going to have to build a transmission line miles and miles, it can look a lot better. So I think some of that is certainly difficult, and as storage costs decline, will probably come into perspective for communities. I think the other thing is, if you're going to do that, one of the major questions is what size of load are you hoping to serve? I mean, are you hoping to service a town that's very far or has limited transmission access? Or are you just trying to service that one farming facility? And depending on that is really going to drive a lot of the questions of how you would make that work.
Okay, your last question, Zach. Thanks for this very clear and helpful presentation. Can you speak a bit to the embodied carbon of solar panels, materials used, and lifespan?
Yeah, it's great. It's a very good question. I think it's always important to keep this in mind. I think as we talk about moving to like low or zero carbon sources, we need to remember this. So I don't know offhand these embodied carbon numbers. I do know that from what I've been told, most of the carbon that's actually in solar, well, there's a couple of sources. One of it is steel, like you have all this racking and stuff. So some of it is about decarbonizing steel production, which we need to do along the way. And some of it is about the electricity that's used in the production process. So what's good about those is those are both kind of decarbonization problems that people are kind of focused on separately. And if we were if we had a decarbonized electric system, and if we figure out how to make steel out of hydrogen or electrical reduction or whatever, we would probably be able to produce solar panels, you know, in a very low carbon impact kind of way. Of course, that's not the state we're in now, and so that is something to keep in mind. I mean, I certainly think that it compares. There's no comparison with any of the fossil fuel sources of generation or anything like that. It's still a fairly low embodied carbon. In terms of lifespan, I think that currently, you know, I think use usually 30-year lifespans as a standard estimate. I will say that a major research focus for us at this time is trying to extend that to 40 or 50-year lifespans. And the purpose of that is really to say, hey, if you're going to, you know, a solar panel or a solar farm has the interesting kind of setup that it's all investment, right? There's no fuel costs. The operation and maintenance costs are usually pretty low, but there's this huge capital cost up front. And so if you can make it last longer, then as an asset, it sort of, the longer it lasts, the more it pays off, and the more that initial capital cost really pays for itself. So there's an effort right now to really improve the durability, but I think 30 years is currently kind of where we aim. Now, and 30 years might be, this is when it's economical to replace the panels with newer, more efficient panels, right? It might not be, you know, that doesn't mean that they're necessarily garbage at that point.
Thank you so much, Zach. It was a fantastic presentation.
This has been a production of Cornell University, on the web at cornell.edu.